Welcome back. So we are coming for the next session for design of feedback controller, PID controller. We start with the presentation. So PID by mathematically. So from the last slide, we have seen that the input to the controller is the error. The error, which is nothing but the difference between the actual process variable with the desired process value or the reference. So if instant if we get a error and that is going to the controller for a particular controller like PID controller, which will develop a mathematical algorithm based on or a function of error with respect to time. So let's see here we can see that this particular error ET is proportional to the the controller output PT is the proportional to the error, and for removing this proportionality we have added one constant, that is Kp. So it is basically Pt equal to Kp into Et, where Et is the error. Now coming for the integral action, it is basically the control output for an integral controller is directly proportional to integration of the error with respect to time, and this Ki is the integral time constant. Next is the derivative control, which is directly proportional to the output of the derivative control is directly proportional to derivatives of error with respect to time. So finally, if we take all three parameters as a combination of the final output from the controller like this V, I and D, so finally it will be summation of all three actions. So what is the all three action summations? It is basically Kpet plus Ki integration 0 to Et dt plus Ad of derivative. So finally, the final thing will come as the ut equal to Kp into Et plus 1 by Ti integration 0 to Te dt plus Td derivatives of error with respect to time. Here two parameters has come, that is Ti and Td. This Ti is basically Kp by Ki. It is called integration time constant, and this is Td, which is basically derivative time constant. So here we can see finally we have a output which is addition of all three control action, which will come for the control signal from the PID controller. So eventually, if you have to get the transfer function, see, as we know, the transfer function is basically in a form of output by input in S domain with zero initial conditions. So if we talk about the transfer function of the PID controller, it is basically the output, which is the control signal, and the input, which is basically the error. So it will be the ratio of these two, and it will give you in the Laplace domain Kp plus for integrator 1 by s, and for differentiator it is s. So finally it will look like this: Kd s square plus Kps plus Ki by s. So this is the final transfer function for our PID controller. Let's say if we have four modes of PID, we can have several modes, but acceptable modes are these four modes. One is P, next is PI, next is PD, and next is PID. So we can have several combination of this proportional integral and derivative controller. Now coming for the most crucial objective, that how we can decide the specific parameter of PID controller. such that we can get our desired output from the process. So we need to follow these steps to get the desired response from the closed loop control output using a PID controller. The first thing, obtain the open loop response. The first most objective before giving to the feedback, first take the open loop behavior to identify what are the areas you need to improve. Next, you add one controller. Initially, we'll add first the proportional controller. If we use proportional controller with this closed loop with the process, first thing it will do, it will reduce the rise time. So that means the response will become faster. Next, some drawbacks will be there for proportional controller. That is nothing but it cannot minimize the offset, the steady state error. So to overcome that, we have to add some other control action also. So for that case, we will add first the integral control action. Immediately adding integral control action with proportional controller, it will act the benefit of the proportional controller like reduce the rise time with the faster response. Same time, nullify the drawbacks of PID controller by eliminating the steady state error or the offset. Next, the drawbacks of integral control action actually leads to sluggish response with adding some oscillation to the process output. So to minimize that or to overcome with that, we'll add derivative control. So by introducing derivative control, we'll minimize the overshoot and improve the system stability. So if we talk about combining all three, KP, KI, KD, which are the major components of PID controller, and by doing a fine tuning on that, we can achieve the desired output of the overall system. See, as I told that we have different modes of PID, so that means it is not always necessary to use all these PID together. We'll add them according to our need. Let's have an example. Like if we have a flow system, a PI controller may provide satisfactory performance without any need for derivative control because it is itself very fast, and because of introducing I, it will reduce the response speed and finally we will get a desirable output. So that is why keep a simple PI controller for a fast process and it will achieve you a desired result. So now characteristics of PID controller, by implementing that what effects will get. So first, as I told that by employing only the proportional controller, the steady state error occurs. It will give the fastest response, reduce rise time, but steady state error occurs. So that is why we have introduced PI controller. The response become more oscillatory. So that is the drawbacks, but it takes it takes longer time to settle. That is why it is oscillatory, but error is disappear. So one disadvantage is overcome, but another disadvantage is introduced. Same time, if we have a proportional integral and derivative control action, so the drawbacks of oscillation and settling time which is increased will be decreased by the derivative action. So combining all these three will get our all design specification to reached. Let's see, in closed loop response, we have this parameter proportional gain, integral gain, and derivative gain. If we increase all of them, what will happen? If we increase them, rise time will decrease for proportional and integral action, but derivative action, it has not that much significant change. It is very small change. Same time, if we increase the proportional gain and integral gain, the overshoot will increase. If a system requires kp equal to 100 value, if we increase it to 300, definitely it will increase the overshoot. Same thing happens for integral action also. But if we had a derivative controller over there, and if we increase the value of the derivative controller, it will decrease the overshoot. So these are the two important parameters. Next is the settling time. Settling time actually gives you that how fast your process is reached to the steady state. So if we increase the kp, if we in just a second, I'll just hmm. So if we need to have a lower settling time, that means faster response. What to change? Actually, that kp value, if we change, there is no significant effect on the settling time. But same time, if we increase the ki, if we increase the ki, if we increase the ki, but definitely it will increase the settling time. Increase because more oscillation will be introduced, so it takes lot of time to settle down. It will increase the settling time. But the only parameter which can deal with the settling time, which will minimize the settling time, that is the derivative control action. By introducing that and increasing the value of kd, you will decrease the settling time. The steady state error, the steady state error is the offset which presents for the proportional controller. If you increase more, it will decrease, but system will get to be unstable. The only controller which eliminate this steady state error, that is the integral control action or integral error. So yeah, how much you increase the ki, it will some instant it will eliminate fully the steady state error or the offset. And these things happens for kd also. These things happens for kd also. If you increase the kd, there is very less significant change in the process output in terms of steady state error. So these are the effect of all three controller PID controller. If we increase the gain of these three controllers, how it will affect to the process. So let's have a look. See, as I told that we will fix the Kp equal to 2. So we don't change the proportional gain. Only here what we will do, we will change the integral gain. Initially, when your integral is gain is 0, Ki equal to 0, that means only P control. See, our desired value is 1 and it has a very large offset or steady state error. So it cannot reduce the steady state error by using only P control. When you have introduced a lowest value of Ki, immediately it's try to nullify the steady state error. See, it's take more oscillation, though it's minimize the or eliminates the steady state error. Gradually, we have increased the Ki from 1 to 2 by fixing Kp equal to 2. We can see more oscillation has introduced, so that means the settling time increases. The rise time also become faster, but system become oscillatory, but more prominently it will minimize the steady state error. Same thing we'll do for PD control. For PD control, as we told that PD control minimize the oscillation or overshoot from the response to get faster response. See, this Kp again we fixed at 2 and gradually we have added Kd. First Kd equal to 0, so we can see more oscillation is there, more overshoot is there. But next instant when we have increased the Kd, see oscillation reduced. Immediately oscillation reduced. So reduced means overshoot reduced, but the set point which is 1, it never reached. The set point which is 1, it is never reached. So what we'll do, we'll increase again the kd. We have increased the kd, but system cannot reach to the desired set value of the 1. So we can see the benefit of d, definitely minimize the overshoot, undershoot, try to become the system faster, but it will uh, it will uh, it cannot reach the desired value. So the steady state error is always present. So next, definitely PIPD have drawbacks. We will introduce PID control to check how they can improve the response. See here we have shown you that three parameters Kp, Ki, Kd all are used, and gradually we have increased them. The first instant where my Kp and Kd is 2, and one case Ki is 1 and one case Ki is 2, right? So when Ki is 2, so gradually when we are increasing the value of Kp, Ki, Kd, we have seen the fast response with lower oscillation and faster settling time without any steady state error we have achieved here when our value all are maximum Kp equal to 5, Ki equal to 5 and Kd equal to 5. So the thing is how we have increased the Ki, oscillation is introduced. But to nullify this oscillation, we have increased same time Kd also. So when we increase the Kd, finally we reach our desired set value. So this is basically operation on PID controller. So when we will design a PID controller for a particular process, definitely we have to play with this parameter to get our desired set value in terms of process control action. So next point, the important thing, the tuning rule. See, these parameter of Kp, Ki, Kd, we cannot choose randomly. There should be a technique or a hard and fast rule such that we can get a definite value by calculating something. So for that, the scientist Ziegler Nichols has given a tuning rule. So this is a open loop method where we have given a curve, S curve, and from that we find out two parameter, one is L and one is T with respect to process output with respect to time graph. That L is nothing but the delay and T is the time constant. After getting this L and T, we can get the parameter of the tuning for my P or PI or PID controller. So these are the table. From this table, we can easily get what will be my Kp, Ki and Kd value for a particular process for which we already got the open loop response. That's why when we have started telling about this designing procedure, first thing we told that check the open loop response, and from the open loop response we will try to think that what are the parameters we need to modify. So this is one example where a spring mass damper system we have introduced, and we will for the spring mass damper system, we will try to find out the transfer function and then open loop response and then proportional controller and then proportional derivative controller. Let's see. So this is basically a spring mass damper system where a mass with a spring and damper is introduced, and we have given a force F, and for that output is the displacement. So if you write the mathematical model for that, that will give you m x double bar plus b x bar x dot plus kx equal to F. So by doing Laplace transform on that, we got the final transfer function of the spring mass damper system in terms of 1 by m square plus bs plus k. So according to the question given in the example, we'll put the m equal to 1, b value is 10 and k value is 20 and force equal to 1 Newton. So that will give you the final transfer function of the system. So now we'll check the open loop response. We have several tools to check this response. I have used here in the MATLAB. So in the MATLAB command window or in M file, you write a script like this. If you write this, you will get a response. So for that response, we'll first introduce P control. For P controller, the transfer function becomes Kp by a square 10s plus 20 plus Kp. And from here, from the given question, the value of omega n given is 17.89. If you use that, you will get the value of Kp equal to 300. So if you use that, so this is now the script to design a feedback controller with PID action. Only P controller will take here. So P value is given 300. So finally we'll get the response. So you can see that there is a better response with P sorry, but it never reached the desired value of 1. Next, we have introduced PD controller. So this is the script for PD controller, and this is for PID action. So we can see for the final response of PID controller, the process is tracked very efficiently, no overshoot, no steady state error. So this is the script. So next day we will try to have another example how we can design PID controller for a particular system. So this is the references. Thank you.